This is Year 14, A22 Physics 5. The synoptic questions. These are past paper solutions from 2004 to 2009. Okay, this is June 04, A23, so it was from the previous years in the old spec. The paper was called A23, and it was Physics 6, and this was the 3B paper. Communication satellites. Geostationary satellites are widely used in telecommunications. They often receive their electrical power by the conversion of solar energy to electricity. A student makes the following statements about a geostationary satellite. Number 1, because the satellite is geostationary, it has no kinetic energy. Number 2, however, work has been done to put it into orbit. Number 3, therefore its gravitational potential energy has been increased. And number 4, the magnitude of the change in p.p.A. is given by mgh, where m is the mass of the satellite, g is equal to 9.8, and h is the distance between the Earth's surface and the satellite's orbit. State why each of the statements are either correct or incorrect, and if any part is incorrect, explain why. So number 1, because the satellite is geostationary, it has no kinetic energy. Now, geostationary satellite is one which rotates with the Earth above the same position above the Earth's surface. In other words, it takes 24 hours for a complete orbit. So therefore, it's definitely moving, and it therefore definitely has kinetic energy. So that's incorrect, because the satellite is moving. And you could write there that the time period is 24 hours, which is the same as the time it takes for the Earth to rotate on its axis. Number 2, however, work has been done to put it into orbit is of course correct. Number 3, it's correct because you have to do work against acceleration due to gravity, or the force of gravity. Number 3, its gravitational potential energy has been increased, and that is also correct because its GPE equals mgh, so h has increased, therefore GPE has increased. And number 4, the magnitude of the change of potential energy is given by mgh, where m is the mass of the satellite, g is equal to 9.8, and h is the distance between the Earth's surface and the satellite's orbit. And this is incorrect. And the answer is because g is not constant. Now, you might see at the bottom of that question there's a mark for quality of written communication, and so therefore you should be writing that in fairly flowing sentences to get your mark there. Part B. A geostationary satellite is fitted with solar panels of area 40 metres squared. The intensity of radiation from the sun at the position of the satellite is 1.5 kilowatts per metre squared, and the efficiency of the solar panels in converting light to electricity is 18%. Calculate the electrical power generated when the solar panels are placed perpendicular to the line from the sun to the satellite. So calculate the electrical power generated. So we know that the received power from the sun is 1.5 kilowatts meters to the minus 2 times 40, which is 60 kilowatts. And therefore the electrical power generated is 18%, which equals 0.18 multiplied by 60 kilowatts. And that gives you an answer of 10.8 kilowatts. Part 2. Assume that the radiation from the sun can be treated as having a single wavelength of 550 nanometers. Calculate the energy of a photon of wavelength 550 nanometers. So E is equal to hf. We're not given a frequency but given a wavelength instead. So we know that the speed of light is equal to lambda f, and therefore f is equal to c over lambda. So that's equal to hc over lambda. And that's equal to, h has got a value of 6.64, Planck's constant, by 10 to the minus 34. C is 3 by 10 to the 8. And the wavelength we're given is 550, and it's in nanometers, so that's by 10 to the minus 9. And when you do that calculation, that comes out as 3.62 to 3 significant figures by 10 to the minus 19 joules is your answer. Part 2, calculate how many photons arrive on each square metre of the solar panels in 1 second. Assume that the radiation strikes them normally. So the amount of power is equal to the energy for every photon by the number that hit per second. So the number arriving per second. So this is what we want, the number arriving per second. So the number per second is equal to the energy, the power divided by the energy per photon, which we've got in the last answer here. So the energy per photon is 1500, which is the same as 1.5 kilowatts is the same as 1500 kilojoules per second. And that's divided by 3.62 by 10 to the minus 19. And that gives you an answer of 4.1 by 10 to the 21. And you would, of course, expect a very big answer there, since we're talking about very tiny particles. Part 3. In 2, we're told to make the assumption that sunlight can be treated as having a single wavelength. Give an example of an everyday observation which tells you that sunlight does not, in fact, have a single wavelength. And that's obviously the dispersion of light. And an example of that is, of course, a rainbow.